All right, let's start. Good afternoon, everyone. And today we're delighted to have Dr. Jia Li as our seminar speaker. Dr. Li is a research assistant professor at Texas Tech University. And this quarter we have quite a few alumni come back to speak, and Jia is also an alumni. And he got his PhD from here a few years back. And he went to University of Texas Austin and did his postdoc for a couple of years, and now he's at Texas Tech as a research assistant professor. So Jia's research interest is in traffic flow, and particularly with connection to connected autonomous vehicles. Jia's education is truly interdisciplinary. I think it's very typical of a TTB and civil grad here, and his bachelor's is in mathematics, and his master's in water resources engineering, and his PhD is in transportation. So that covers a whole range of topics. And I think either he or I haven't figured out to talk about traffic flow without some equations. So you have to bear with him with some equations, and you're getting an engineering degree, so you should know some of them, right? Okay, without much ado, let's welcome Dr. Jia Li.
Okay, thank you for the introduction, Michael. And I graduated from here 6 years ago, and it's a little bit nervous to stand here and on the other side. So today my topic is heterogeneous traffic flow. How the agent behavior shape the collective properties. So I want to first give you some idea of the research. So I first want to give you some idea of the research that I'm doing. And for overall, my research region is that I am interested in the interactions of humans and autonomous agents. We know that in transportation, the autonomous vehicles are becoming, technology are becoming more and more mature, and we anticipate they play a very important role in the transportation system. So, but at the meantime, we anticipate there will be some conflict and incompatibilities between the autonomous vehicles and the human-driven vehicles in our system. So my vision is that how we can identify their potential conflicts and resolve them and make our overall system better. And specifically, I'm focusing on two topics in my research. So my first topic is on the traffic flow problems. That's also the topic I focus on in my dissertation. And some motivation for this topic is that the time when I graduate and get my PhD degree is the time that when the autonomous vehicle driving technology become mature. And at that time, I joined the Center for Transportation Research at UT Austin, and I happened to on several projects sponsored by the Texas DOT. And I got to know some operational challenges and the modeling issues and the technology advance in this area. So I'm thinking that traffic flow theory would be a very powerful tool to model how the flow would be and anticipate their impact. So that's my first topic. And under this topic, what I'm going to cover today is primarily about interaction of AVs and HVs. Here, HV refer to the human-driven vehicle. And another topic that's related to the modeling of their interaction is how we can develop a control strategy that let the traffic flow self-organize and self-stabilize. So the vision here is that we anticipate some change in the control paradigm for the traffic flow. Because nowadays we know that we rely on centralized control strategies, such as traffic signal, ramp meter, and the speed limit, etc. But the vision here is that with the automated vehicle, we can do things more decentralizedly, in a more decentralized fashion. and explore how we can change their individual behavior to achieve certain system objective. So that's about the traffic flow problems. And the second problem I'm focusing on is the ride-share market. And that I started this topic after I went to Lubbock. So if you do not know Lubbock, it's a small city in the West Texas, and it's there is some population there, but it's very remote from other places, and it's a typical small community that you can see. And my interest in this is that how we can characterize the dynamics of the restaurant market when the market sickness is seen, referring to that you have limited demand and supply on both sides of the market. And on this topic, I apply actually some tools from the traffic flow theory. I used the queuing models on this topic, and my specific interest is on what is the dynamical property that we can anticipate when we change different parameters. Now, for example, here you will see some bifurcation behavior when we change the market sickness, and that will have some implications on how you should maintain certain size of fleet to keep the market self-sustained. So that's my two of my current research topics. And, my primary focus are actually at two scales. So for those of these two problems that I currently study, one scale of interest to me is the interactions between the different agents. So for this, I adopt a multi-agent perspective, and I like to track the behavior and activity of different agents. And on the other hand, I'm interested to know the system behavior, which can be both a traffic flow system or ride-share system. And I'm in particularly interested in the connection of them. That is how the individual agent behavior or interaction can result in certain system performance. So that's about the overall vision of my current research. So let's go back to today's topic. Today we are going to cover heterogeneous traffic flow. And so what's the motivation of study heterogeneous traffic flow? So we know that even though we have the classical traffic flow model, such as the LWR model, which assume that all the drivers are identical, but in reality, what we see is that traffic flow always exhibits certain level of heterogeneity, right? So, for example, the vehicle dynamics could be different. That refer to on the road, you can see cars and trucks. They have different vehicle performance. And we learn in the transportation engineering class, those different vehicle performance will result in different roadway design. And also, the driving style could be different, right? Someone would be more aggressive in driving, and you can see on the freeway, some drivers keep overtaking other drivers, but some others will tend to follow the vehicle that is leading. So we have different characters of drivers, and they have different driving style that's exhibited in the traffic flow. And also, we know that one of the important motivation of this research is the level of automation. So we have the human drivers nowadays, but we see already the automated vehicle has gone to the road and mixed with the human-driven vehicle. So we can anticipate a very long transition period that human-driven vehicle and the automated vehicle will share the right of way. So, so that's another motivation of this research. That's because now we do not really have the empirical data to know how they interact. can we use mathematical modeling to make certain forecast and get insight into their interactions? So that's another another motivation of this research. And so as for the effect of heterogeneity, so is heterogeneity a good thing or bad thing for traffic flow? That's really not there isn't a simple answer to that. So we can have examples like in the highway traffic analysis. We know that if you have highway vehicles mix in your traffic flow, in general, you will have worse performance for your overall flow, right? Because the truck will drive slowly and cannot tackle the curves very well. But on the other hand, if we have the mixed vehicles, we can also utilize some of the vehicle within the traffic flow to stabilize the overall flow. So that means there are actually two sides of the story for heterogeneity, depending on how the different agents interact. So that's some basic vision for this research. And so this come to the to the main perspective of this research. That is the design of the interaction is crucial. So if our traffic flow consists of all human drivers, we actually can observe how they interact, but we do not have much control of how they interact. That's for the human-driven traffic flow. But when we have the automated vehicles on the road, somehow we can imagine, we can design the protocols of how they interact, right? Like we design the protocol of how data transmit over the internet. So that gives us the possibility of design the interactions of human-driven vehicles and AVs. So that's some ultimate goal that I want to achieve through this research. So some particular interesting aspects of the AV and HV is that in the first, out of the practical consideration, we can anticipate a very long transition period that AVs gradually go onto the road, but do not replace the human-driven vehicles completely. And we know there is a life cycle for all the human vehicle, which is about 15 years, and also due to the public preference on the human-driven vehicle. So this period could be very long. And another especially intriguing aspect of the AV and HV interaction is that we can anticipate, because AVs here, I assume they have the communication capability. That is, they can talk to each other and they have certain intelligence to make decisions collectively. So that means on the road, we potentially will see some cooperative behaviors of AVs, and that is different from human drivers. Recall that regardless if of your vehicle dynamics or driving style, nowadays human drivers, they do not really have systematic mechanism to cooperate. But on the future road, we can imagine the potential scenario that AV will develop a certain cooperative mechanism between them. And so this leads to the goal of the research. That is, if we can know what behavior will the connection of the individual behavior with the system performance, we can develop design for the AV behaviors. So that will improve your overall traffic flow. And that's some basic vision about this research. And in particular, in this talk, what I'm going to cover is that I will propose some analytical model to depict the equilibrium reached when AVs and HVs interact. And actually, the model is a little bit more general than that. It will cover some existing model on the interaction of a passenger car and the trucks. So it's a general framework that I propose. And so some practical motivation is that specifically when we have AV and HV, how the road capacity should split between them, right? And if they are cooperative between themselves, will they form certain traffic pattern on the road? And so is there any implication for the lane control policy? So that's something I try to answer through the analytical model. And in particular, this research contributes to the current state of art in several aspects. So compared to the current model, the proposed model explicitly consider the role of lanes in the mixed traffic flow dynamics. And another thing that is very interesting is called type sensitivity, meaning that how vehicle are aware of the leading vehicle's type and determine its own speed spacing relation. And I will show that this type sensitivity is actually something that can influence significantly to the traffic behavior. And another thing is that we know that AV can switch between the full automated mode and a semi-automated mode. So depending on the surrounding vehicle. So this adaptiveness is also something I look into in my research. So to give you the idea of how I develop a model, let's first review some basics from the traffic flow theory. Now, we know that LWR model is the most classical model to model traffic flow, right? And it's basically the most important assumption is as shown in this figure. You assume there is some relation between the flow and density, and that's the so-called fundamental diagram. And then essentially, we know that this fundamental diagram specifies the longitudinal propagation of traffic flow, right? But it doesn't consider any behavior across the lanes, meaning the lane change or lane selection, etc. So that's the basic perspective of the LWR model. And to address heterogeneities in literature, there are actually different type of extensions to the LWR model proposed. And, let's see here, in the mixed traffic flow, we can assume without loss of generality, we have two types of vehicles, and they could have different flow density relationship. And those relationships encapsulate their behaviors, right? So for example, in this figure, we can in general interpret the upper line, the upper fundamental diagram refer to the diagram for passenger cars. The lower one represent some diagram for trucks, right? So that's just for illustration. We can have the agent that is endowed with different fundamental diagram, and that will be the basic starting point to model the heterogeneous traffic flow. And the descriptive approach of extending the LWR model is actually a very straightforward extension. So LWR model, we have one equation, right? It's about the conservation equation for the traffic density. And in this descriptive extension, we have two equations. Each one model the propagation of one traffic stream. And we see in such model, the coupling occurs through the function of Q, right? So this is an extension of the single class fundamental diagram. We usually call it flux function. So the coupling mechanism is encapsulated through the flux function. And the early examples for such study usually directly prescribe certain form for this function. And this is some example that means the split of your flow will be influenced by the proportion of your traffic. And also, this is the nominal fundamental diagram shown here. So this give you the idea of how we can make the extensions to the LWR model, which is a classic single class model. So this similar approach was used to model AVs and HVs. So the basic idea is the same, but they assume a different function form for such flux. And we can imagine what's the limitation of this approach. So this approach is entirely based on the aggregate flow, right? And from this, we cannot directly tell what's the specific driver level interactions. And also, we do not see how the lane policy will influence the coupling, right? So in such model, in the descriptive extension of the LWR model, we have some model of similar form, but we miss some important policy considerations. That is the interaction of agent and the lane policy. So these are two important things we want to consider in our model. So there is another approach that consider the behaviors of agents, and I call that behavioral model or semi-behavioral model, depending on the details incorporated in such models. And the big difference of such model from the descriptive model is that rather than specifying some flux, we will use the agent behavior principle to construct flux. So that's the important difference of such model and the descriptive model. And here, I will not give you the full detail about every model, but want to mention that in such model, we can account for the agent preference and how they interplay with each other. And also the lane policy, such as dedicated lane or priority lanes. In such models, we can see some early examples in 1990s when special lane is considered. And also there's the interest to extend in the recent years. So if we only consider the agent interaction, for example, through introducing the user equilibrium principle, but ignore the lane setting, we have the semi-behavioral model. Such model is appealing in that you gain some benefit in the computation, but still you do not model the lane policy in such models. So back to our topic, what I propose today in this topic is in this talk is an analytical framework to do several things. So first, I want to explicit consider the length, the role of lane in shaping the interaction of AVs and HVs. And another thing is that I will assume the agents are endowed with heterogeneous speed functions, which are general. I do not want to limit attention to the specific form of speed functions. And the last, as I mentioned, that the agent type sensitivity will be considered. And this is something particular to the HVs. And as I will show, you will see some very interesting properties when the type sensitivity property is considered. So overall, what I do is that I want to seek the equilibrium speed for mixed traffic flow in the following cases. I will first start with the single lane case, and then I will discuss two lane case and extend that into the general n lane case. So that's the basic structure of this talk. So in the single lane case, let's imagine a scenario how we can get the equilibrium state of a system. So one approach is that you can consider if you have a closed system without exchange of flow or information with the external world, and you can let such system to run infinitely long, and then finally the system will settle at a certain state. Nothing will change, right? So this is the equilibrium that we usually refer to. Now here, the situation that I consider is that I consider a circular road. So meaning that no overtaking is allowed. Just one vehicle follow another. So there could be potentially the constant oscillation in such system. But a very most probable case at the equilibrium is that all the vehicles will settle to the same speed in this case. So this is the situation that we can imagine at the end of the time. So if the circular road, the total length is 0, because vehicles in each class will have the same speed. So they will have the same following distance, right? So we have this equation that just tell you the total length of the road is equal to the total spacing between vehicles, right? So so here we can do some translation, assuming that spacing and the row have the relation that spacing is 1 divided by density. So that's some common assumptions you make in the traffic flow theory. And because we know each agent is endowed with a speed function, so we can replace this function here, and the V star is the unknown equilibrium speed that I have, right? So this gives you the total length of the road is equal to this the sum of these two terms. So in this, we can see the only thing unknown is your V star, right? The equilibrium speed. So this basically gives you a definition of the equilibrium speed, and you can actually divide both sides by L, and you can get this this first formula, which defines the equilibrium speed. And actually, it can be shown when your V1 and V2, that is the speed function you give to the two type of agents. From this, you can always solve a V star, and the V star is always a well-behaved function. And essentially, this gives you certain interpolation of the wave of the speed between the two type of agents. So that's the essence of the problem. And we see this is a very simple scenario, right? So in this case, we ignore a lot of things. We do not consider overtaking. We do not consider the lateral distribution of agents. And we only consider their following behaviors. And one thing important here is that the speed is actually only a function of spacing, but not really the vehicle type. So this motivates the research that consider a more complicated scenario of addressing the vehicle type's influence on consecutive vehicles' following speed. So this is a very natural motivation, because consider if you have automated vehicle and it's following another human vehicle or following its own type of automated vehicle, then the behaviors will could be different, right? Because in the latter case, you can have a shorter headway because of the connection between them. So that's the motivation of in the AV context, we should consider the type sensitivity or type awareness. So in this case, we actually see we can do something similar in the same rationale, but here rather our vehicles will fall into 4 groups, right? Depending on the following relations, because we have 2 types of vehicle and they have 4 types of following relations. So that we can have a similar equation to the thing that we just had, and after some algebra, you can get something very similar to what you have in the previous slide. And this is the final formula that you get for the equilibrium speed of the when you consider the type sensitivity. So we do not see much difference here, right? we only have more classes of vehicles that we have. But in this case, this is not so useful because it's not an explicit formula for us to infer the vehicles, the flow's behavior. But something we can see is that the total number of vehicle is rho, and the sum of rho ij over all the I and j should be equal to the total density, right? So that means the split of the rho into the rho ij will determine your mixed flow speed. So that's some physically intuitive idea, right? So in another word, when the vehicles are type sensitive, how they mix will influence the mixed flow speed. So that's something different from the human driven vehicles. So we can go on with the formula and do some simplification. So here, in this page, we can see that rho ij is something unknown, right? So in theory, you can have arbitrary distribution of rho ij into 4 classes, and as long as their sum is equal to your total density. So we want to get some estimate of the rho ij so that we consider, in this case, if we randomly distribute vehicles on a circular road, what's the probability of different type of following relation occurs? And this actually give you an approximation of such relations. So basically, this means if you have class I agent and a class J agent, then the probability of class I following class J will determine by the percentage of S agent. So this is the formula that we have, and you can see it's entirely symmetric with respect to the 2 types of vehicles. So this will allow us to calculate the expectation of the rho ij for I and j equal to 1 and 2, right? So we get these four estimations, and we can plug this into the formula that we just have, and we get a formula that is slightly explicit than the formula that we have. In here, you have the total density, and you have the rho I and rho j, which should be given, right? Because you in this system, you know the number of 2 agents in the system. But still, we want to make some further simplification to get insight, and this is what I do. So here, I will assume all the speed function for the following relation ij. I will assume it's parameterized by a parameter aij. So this parameter will encapsulate the driving technology and the cooperations between agents. So we can understand this by thinking of some special examples. For example, if aij is equal to 1 for all the I and j, then that means we have homogeneous traffic flow, right? Now, if we have the aij larger, then the corresponding speed function will tend to be larger, right? So that means your vehicle can drive faster under the same headway. So the larger A here actually refer to a better technology. And also the cooperation between the consecutive vehicles is captured also through the aij value. And I will give you some example so that you can understand in the following. And this is the formal definition of type sensitivity. So we call a class I agent type sensitive if it has different values when the j and j prime is different. So meaning that I will change my following behavior depending on the leading vehicle's type. So that's called type sensitivity. So otherwise, a class is called type insensitive. So this turns out to give us a big advantage to simplify the previous speed function that we have. And after some manipulation, you can get a function like this. So this v is the nominal speed function you define here. And the mixed flow speed when you have rho 1 and rho 2 will be determined by the percentage of rho I and rho j in the entire traffic flow, and also your technology factors that influence their behavior. So this gives you some idea of how in this relatively simple system, how different factors come into play. So, to further understand what the model suggests, I will give you some example problem. So let's consider if we have a constant total traffic in the system. So meaning that rho 1 plus rho 2 is equal to some constant value. And we denote their percentage respectively as a p and 1 minus p. So I will consider when I have this total density, when I can get maximum or minimum value for the speed, right? So that is a kind of a design problem. So when you have a system and you know the total density, so how you can control the proportion of your vehicles in the system to achieve certain performance. So in the first case, let's see, when we have A11 larger than A12 larger than 1, and A21 equal to A22 equal to 1, then we have the maximum speed will be attained at p equal to 1. So here, the interpretation is that for this case, we see that this is type insensitive, right? Because the coefficient is the same when you change your leading vehicles. And this represents some typical human-driven vehicle. And this actually means that class 1 vehicle, when following class 1 vehicle, the maximum speed will be attained. So this model A11 model the case when an automated vehicle follow an automated vehicle. And this model, the automated vehicle following a human-driven vehicle. So this number is smaller. And this, when you have this condition, you can verify the maximum system speed when your p is equal to 1, meaning that when all the all the traffic are automated vehicles. So this is kind of a trivial example, right? And that's also something we imagine when we have 100% automated vehicle, we have the best traffic performance. In the second example, the case may be more interesting. So in this case, I consider the scenario when A11 is equal to A22, and A12 is equal to A21 equal to 1. So, so this model, the scenario that when you have two groups of AVs, for example, by different manufacturers, and in this case, the AVs from the same manufacturer will have the maximum benefit when they follow each other. But when they follow the AV of the other manufacturer, you don't have as much benefit. It's just as you are following some regular vehicle. So in that case, something we can get is that this system will have the minimum speed when p is equal to 0.5. So the interpretation is that when you have all the AV vehicle, but they do not cooperate on the road, then your speed will be minimum when they have the equal weight on the traffic flow. So my interpretation of this is that when you have AVs but following each other across the class do not offer any benefit, then when they have the equal weight, they tend to interrupt the other vehicles to the maximum extent. So that's the interpretation of this result.
So p equals to 1 still give you the maximum speed?
I didn't verify that. I can. But
if it's uniform, if it's only one.
Yeah. I think that's the homogeneous case.
Right.
When you have p equal to 1. Yeah, I think that's right.
P equal to 1 or p equal to 0 should be the same, right?
Yeah, it's symmetric. Yeah. So this give you some idea that your overall traffic performance in the system not only depend on your percentage of AVs, but also, and more importantly, which a lot of work overlook, is that how they interact. So their specific way of interaction will actually influence how the traffic perform. So that's the point of these two examples. So that's finished the part of the traffic flow on a single lane road. And now let's go to consider a more complicated scenario, that is the mixed flow when we consider multiple lanes. So this is something missing from most existing mixed traffic flow models. And what I propose here is that I cast this problem as a two-player game. So imagine that each class of the vehicle will correspond to one player. And this player, what they do is that they want to split the road capacity between them. So their strategy side is the lane groups they occupy, right? So in the two-lane case, assume we have two lanes A and B. So for each class of vehicle, there are three possibilities, right? For example, here the class 1 vehicle will occupy lane A or lane B, or occupy both lanes. And similarly, for the player 2, I have the symmetric response. And the thing that we can do here is that we have all the non-possibilities for the distribution of traffic flow. And for each of the case, we can characterize what's the corresponding speed for player 1 and player 2. And this gives you the payoff function for this game. Right? So this is a static game that as long as you get the payoff by a matrix, you can totally characterize what's the equilibrium they reach. So that's the idea I apply here to look into the distribution of traffic on the two lanes. And here, as a most work in the game theory, I will search the Nash equilibrium for the distribution of traffic over the two lanes. And here is something that I will not go into detail, but this tells you the condition, all the possibilities of equilibriums that you can reach. So actually, it can be proved that if your speed of the mixed flow doesn't meet one of the conditions, then definitely you can find another situation or another distribution of traffic that will improve your traffic flow. So that's the application of the two-player game to characterize the mixed traffic flow problems. And the key thing here is that you want to have a proper strategy side and get the payoff functions. And similarly, for the case of N-lane road, we will have a similar scenario, but the difference is that we cannot enumerate all the possible combinations of lane yields because the number would be very large. So here the treatment is that I assume the total number is n, and I introduce two parameters to describe the lane yields, which refer to the percentage of lanes this class of vehicle occupy. So there are two cases I can consider. So when P plus Q is equal to 1, that will define some separation of the vehicles. So you put the class 1 vehicle into the P multiplied by N road. The remaining capacity will be allocated to the class 2 agent. So that I refer to as a separate state. And in the second state, second type of state is called mixed state. So in this case, you also have the N multiplied by P lanes dedicated to the class 1 agent, and N multiplied by Q to the class 2 agent. But different here is that you have certain lanes reserved for the mixed use of the two types of agents. So this still will be cast as a two-player game, and we will seek the Nash equilibrium of this model. So the difference here is that I will use the PQ, which are continuous, as the strategy by the two players. And the payoff function still is the speed corresponding to the different values of P and Q. So here, the one major finding is that when the vehicles are not type sensitive, then the one pipe speed from the one pipe speed will be independent from the specific way of lane allocation. So that means when the vehicles do not respond to the vehicle types, then the specific fashion that you allocate your traffic to the different lanes will not influence the one pipe speed. Now here, one pipe speed refer to the equilibrium state that all the vehicles travel at the same speed. And more specifically, we have some characterization of the one pipe regime like this. So still, we assume that your speed function is governed by scaling parameter A. Then in the one pipe regime, the speed is this value, and it will take within this regime. So this gives you the idea of how a type insensitive vehicle will behave. So and this theorem summarizes what I just said, that when mixed flow consists of type insensitive agent, the one pipe speed will be uniquely defined, and the lane allocation will not play a role in determining this speed. So it's only depend on the density and your parameter that capture the technologies. So here we can do a visualization of the type of equilibrium we can reach. And here what we consider is the PQ space, which represent the strategy space that your two player get into play. And basically what this means that you can find a line OI which represent the equal speed of the two agents. And within this region is the case when you have the mix use lanes. So within this region, how you do the lane allocation or lane policy will not influence the performance of the traffic. So that will potentially provide some hints of how we design lane control policies. So that will not only depend on the percentage of different vehicles that you have, but also you should consider how vehicles interact with each other. So that's some possible insight we can draw from this equilibrium structure. So here I will give you some example. I consider AVs and HVs on two-lane road. The one of the lane is the AV lane and the other is mixed-use lane. So ultimately, we want to construct some equilibrium relation that capture how they interact. And this in this example, I consider that AV can switch between two modes. That is, it can follow HV with a larger spacing, or follow the AV with a smaller spacing, and that respectively correspond to the ACC and the CACC mode. So this is the type of relation you can derive when you consider the interactions. And as we can see, this represents the density of the two vehicles, and this splits your total state space into two parts. So in this part, you have the two-pipe regime, which refer to that your vehicle can travel at the same speed, and they are both satisfied with their current speed. And in this part is one-pipe regime, so the vehicle will travel at the same speed, and no vehicle can improve speed by switching lanes. So something we can tell is that for mixed flow, we no longer have the simple fundamental diagram as we see for the LWR model, but rather we have some two-dimensional structure in the speed density relation or in the flow density relation. So that's will call for some more thorough consideration of how we design the control system for the mixed traffic flow. So this is some more complicated equilibrium relation we can anticipate, and this give you the numerical realization of this example. And the two we can see match the patterns match very well with each other.
So the first graph is speed and second is flow?
They are both speed, but for different class of vehicles.
Yeah.
So what is the protocols or the rules for the AV lane?
So in this example, AVs and HVs are both self-interested, meaning that they will do whatever they can to maximize their speed. So that's also the intent of introducing the Nash equilibrium. Right? So they are selfish drivers. So okay, I think the time is good. So now is the summary and the future works. So in this talk, I give you introduction of the analytical framework that I propose, which try to capture the impact of agent behaviors on the flow equilibriums. So that's I try to bridge what we see and what we can modify microscopically to the macroscopic dynamics and the behavior of the system. So that's the primary motivation of this research. In the single lane case, we discuss the type sensitivity, the influence on the mixed flow speed. And in the multi-lane case, we formulate two-player games and draw insights into under the assumption of Nash equilibrium. What's the traffic pattern that we can get? And as for future works, I think there are a lot of things that we can do. And some problem I can think of is that first we can consider the asymmetric agent behaviors and the lane preference, because as you can observe on the real world freeway, different vehicles may have different preference over the lanes, and the utility of different lanes may be different to different agents. So this could be captured in more sophisticated models. And also in here, we use the Nash equilibrium, which is a pretty standard hypothesis in economics. But in traffic flow, I think we now have enough data, for example, the NGC data, to validate such hypothesis. And that can possibly reveal more realistic human behaviors in the traffic context. And the last, but I think that's not least, is that we, as long as we have the characterization of equilibrium relations, we can went one step further to consider the dynamics. And in dynamics, we can have more interesting behavior to model. For example, the opportunistic behavior that if my AVs are very opportunistic and try to switch lane and keep improving the speed, will that be beneficial to the overall traffic flow? So that's something intuitively, the answer is no, right? Because for the traffic flow to perform good, you want certain cooperativeness and limit the selfishness of the vehicles. And another thing is that if we can design the AV behaviors, can we design specific behavior that can enable them or incentivize them to form platoons in the traffic flow or form other flow patterns we like. So that's the self-organized effect of the heterogeneous traffic flow. So that's all for my talk today. Thank you for your time.
So we'll open up to questions, and I'll remind Jia that because we're recording the presentation, so you'll repeat the questions first before you answer all the questions.
So in the last example, how do you differentiate ACC and CACC? The head rate difference or speed?
Yeah. So the question is that in this example, how do I differentiate ACC and CACC? So the difference, the detailed treatment is that they have the different head weights, and that's reflected in the fundamental diagram.
You mentioned about like the Nash equilibrium. So if you're talking about Nash equilibrium in KV and HV, then the socially efficient outcome that comes out from the Nash equilibrium is less than what the society wants. So in your case, like what is the less efficient point from the Nash equilibrium?
So your question is that what's the least?
Yeah, the least desirable point from.
Okay, from the Nash equilibrium. Yeah. So I think that's interesting question. So you try to jam the freeway, right?
Yeah.
Okay.
Yeah.
So I think intuitively I didn't have the rigorous analysis, but intuitively you want the slow vehicle to occupy all the lanes, right? Imagine you have two trucks and they want to block the road. You want to allocate them to each of them to one lane, right? So that's something I can imagine. In the worst case scenario, I imagine you can do very bad.
That actually happens in real life. We have rural highways, just 2 lanes in each direction. The passing trucks takes a long time.
Yeah.
So they're behaving like the worst Nash equilibrium.
Yeah, exactly.
And then the long queues will queue up behind these passing trucks.
Yeah.
Let's first.
Your approach when you are using the Nash equilibrium and you have the game between the 2 players, how are you sure like that the equilibrium doesn't? So maybe the core of the game is empty.
So you mean like in the Nash equilibrium,
they made damage. So in that game, how are we sure like the equilibrium doesn't exist?
okay, I cannot ensure that. So
Can you repeat the question?
So the question is that how I can ensure the existence of solution to this game. Is that right? So my answer is that you cannot really ensure the equilibrium exists. Now here, what I do is that if the equilibrium exists, what's the condition for the possible equilibrium? But I didn't look into the existence of natural equilibrium. So in certain scenario, I imagine that there isn't a natural equilibrium.
So is there a way to allocate a payoff in all of those that play against on that state, on the matrix that you had?
So in this,
Yeah.
So-
Is there a way to like allocate payoffs?
so the payoff here is defined as the traffic speed. And here, if I know the allocation of traffic to different lane group, I can calculate the corresponding traffic speed. So that's the payoff function.
But you can always make it stochastic game. It doesn't have.
Yeah. So there is the famous conclusion that for the game you always have a mixed type equilibrium.
Question about the P and Q, the portion of the vehicles. So how do you ensure n times P or n times Q is a discrete integer value of the lanes? Right? N is total lanes.
Okay, so here the question is that how do I ensure the n multiplied by P and multiplied by Q is an integer? So
What does it matter?
the answer is I cannot ensure that. The point here is that when n is large, the rounding will be close to this continuum treatment. So
Any other questions?
One more. So you mentioned about like the static gate, yeah. So but in a lane in a highway, suppose like both of the parties are like self-interested. So they are like more into like dynamic gates.
that's a great question. So
Can you repeat the question?
so the question is that in a real freeway, so it's more close to dynamic game. So is that right? So I think you are correct. In the dynamic context, when we consider the dimension of time, you will see a lot of more interesting behaviors like anticipation and computing over the time. But this work is more illustrative and try to capture if everything is steady, what the condition will be. Yeah, but if you consider the real-time control, obviously the dynamic game will be more realistic approximation to the problem.
In other words, it's the first step. First step to look at from the simplest case, you can look at these relationships, and then once you understand that better, you can move on to dynamic.
Yes, and one thing, the analogy that we can draw is that in traffic flow, in 1930s, people discovered a fundamental diagram, which is about equilibrium, right? And the L-diagram model was discovered, established in 1950s. So that's about dynamics. So pretty much the rationale here is that we first try to understand the simpler condition and then have the more complicated scenarios.
Right. I think Jia assumed that you took 256. No, all of you, and so if you took 256, you at least understand half of it. But if you didn't take 256, you probably only thinking, oh, autonomous vehicle, human-driven vehicle, autonomous vehicle. So they're playing each other as a game, right? So, any other questions?
Okay, so I'm one of those people who is very much a planner, not an engineer, and so I'm not going to ask anything about the technical piece of this. But looking forward to policy implications, does it look like your research is showing that we ought to have separate lanes for autonomous vehicles, or can there still be a net benefit if autonomous vehicles and human-driven vehicles are mixed traffic?
Yeah. So the question is that from the policy perspective, whether it's beneficial to have dedicated AV lane, right? That's a great question, and that's actually one of the major motivation I have when I initiate this research. And, from my model, what I want to highlight is that it's not really a simple question, but really depends on how specifically the AV and HV interact. And the type sensitivity I cover here in this talk is one example of the interaction. And in reality, you can expect more complicated interactions. So I think as for policy implications, we should have more thorough thinking about the potential interactions and the impact, and then not only depend base the decisions on the percentage of AVs or HVs. That will be a too simplistic decision, I think.
I want to add to that is because you could, let's think about it. If you have a railroad and people, just like race cars, they keep on traveling there and never get exit, just going on and on. Then obviously you separate them, it's better, and because the AVs travel faster, so you can put a lot more flow, right, to separate them. But if you have only fewer AVs, it doesn't make sense because they occupy the road and it's most of the time it's empty, right? So it really depends on, and also in real life you have entry and exit. So these AVs cannot go on the belt road and go on round and round forever. So they have to enter and exit. So you have to mix with others. So it really depends on the situation and also on the demand, right? So it's not a yes or no question.
Thanks.
Do you see a possibility of this type of analysis being applied in a more urban setting where you have more different types of vehicles, transit vehicles, pedestrians, crossing, bicyclists, or is it more limited to highway type situation?
Yeah, so the question is that if the current analysis can be extended to the urban scenarios considering transit, pedestrian, and bicyclist. So my answer to that is that I do see some more immediate extension to consider transit in this type of model because that can be readily modeled as another class of agents in this. But as for the interaction with pedestrian and bicyclist, that could be more complicated because the interaction not only occur according to length, but it's more the two-dimensional thing. And I think that will need some more further thinking about that.
Any further questions? So if not, we'll stop here. We want to thank Jia Li again for. Don't forget to post your questions on Canvas. Right?